Let's dive right in, shall we? Today, we are exploring the absolute bedrock of scientific measurement, the very foundation that makes all of physics possible. We're talking about units, dimensions, and the strict rules that allow us to consistently describe the physical world around us. Because think about it, without these concepts, every single scientific discovery would just be an isolated guess. There'd be no way to share knowledge. So, let's hook our focus right here on this grand question. How exactly does humanity quantify reality? I mean, how do we zoom all the way out to the vast cosmic scale of galaxies, and then zoom all the way down to the precise mechanics of kilograms and meters? Well, every measurement you will ever take has two crucial parts. First, you have a number that expresses the magnitude, and second, you have a standard unit. Today, in this explainer, we are going to unpack exactly how those standards are set, how they're maintained, and why they matter so much. And our ultimate guide for today's journey is a true gold standard text, the NCERT Class 11 Physics textbook. We are going to be walking through its core principles practically line by line. We'll pair that with some rigorous error analysis guidelines to give you a truly definitive, rock-solid understanding of physical quantities. Here is our roadmap for the explainer. We'll start with the need for units, move into the art of precision, tackle dealing with errors, uncover what dimensions actually are, and finally, we'll see dimensional analysis in action. Okay, Section 1. The need for units, from chaos to SI. Let's see why we absolutely fundamentally need consistent standards to prevent total scientific chaos. Because for centuries, scientists across different countries were using entirely different systems, which, as you can imagine, made sharing knowledge incredibly difficult. Just look at this timeline. Tracing this historical evolution, we can see the vital shift from arbitrary, hyperlocal measurements to a globally accepted system. In the past, we had the British FPS system. That's feet, pounds, and seconds. We also had the CGS and MKS systems. But here's the thing. With the rapid, explosive development of science and technology, especially when folks started diving deep into electricity and thermodynamics, just having length, mass, and time simply wasn't enough. So the MKS system was heavily improved and extended into what we now call the SI system, which was formally established and recently revised by the International Bureau of Weights and Measures. It's coherent, it's rational, and best of all, it uses the decimal system, which makes conversions beautifully, elegantly simple. Now, the absolutely crucial point on this table is that these 7 fundamental base quantities are the primary building blocks for every single measurement in the universe. Literally everything starts right here. We've got length in meters, mass in kilograms, time in seconds, but then, as science expanded, we added electric current in amperes, thermodynamic temperature in Kelvin, luminous intensity in candelas, and the amount of substance in moles. These are the fundamental units. They are completely independent of one another, and they form the absolute foundational base of the entire SI system. But what happens when you need to measure something a bit more complicated? Well, think of derived units like a recipe. You just mix together those fundamental base units to express complex physical traits. Take speed, for instance. Speed isn't a base unit. It's derived by dividing a base unit of length, the meter, by a base unit of time, the second. That gives us meters per second. It's that simple. All other physical quantities you'll ever encounter are just combinations of those magnificent 7 base units. Moving right along to Section 2, the art of precision, and specifically significant figures. We have to talk about this because out in the messy, real world, no measuring instrument is perfectly exact. The result of any measurement is only ever an approximation, and we have to be incredibly honest about how precise our tools actually are. We formally communicate this level of precision using what we call significant figures. Basically, they represent all the reliably known digits in a measurement, plus the very first uncertain digit. And doing this prevents us from reporting absurdly misleading data. For example, let's say a pendulum oscillates for 1.62 seconds. The 1 and the 6, those are certain, but that 2 on the end is our first uncertain digit. If you were to write it as 1.62000, you would falsely imply a level of laser precision that we simply do not have. As you can see here, converting these numbers to scientific notation instantly clears things up and tells us exactly how many meaningful, significant figures we are actually working with. I want you to really absorb these rules, because this is exactly how scientists prevent errors from artificially inflating their precision whenever they do math. Let's say you divide a mass of 4.237 grams by a volume of 2.51 cubic centimeters. Your calculator, which knows absolutely nothing about physics, will spit out a density with something like 11 decimal places. But wait, Your volume only had 3 significant figures. So rule number 1 swoops in and dictates that your final answer can only have 3 significant figures. Remember this golden rule. Your result cannot ever be more accurate than your least precise measurement. Which brings us nicely to section 3, dealing with errors, embracing the flaws. What's really fascinating is how physics actually handles the unavoidable fact that every measurement is inherently flawed. Because even with perfect significant figures, the basic physics of your experiment, the skill of the observer, and the physical limits of your apparatus will always introduce some level of uncertainty. By comparing these two main types of errors, we can actually learn how to mitigate them. Systematic errors are consistent, they're predictable. Think of it like using a steel ruler out in the freezing cold. The metal shrinks, so it will consistently overestimate the length of whatever you measure. But here's the good news, you can correct this if you know what's happening. Random errors, on the other hand, are totally unpredictable. They are just the unavoidable background noise of human observation and tiny environmental fluctuations. We minimize random errors statistically, usually by taking a measurement over and over again and calculating the average deviation. And there's a vital concept to grasp right here, the instrument limit of error. In plain English, this simply means your measurement can never ever be more accurate than the tiniest tick mark on the tool you are holding in your hand. If your meter stick only has markings for every millimeter, your least count is 1 millimeter. Sure, you might be able to sort of estimate half a millimeter by eye, but that millimeter mark represents the absolute hard boundary of your tool's capability. And let me tell you, the stakes get much higher when we start doing math. When individual measurements are plugged into formulas, their unique errors actually compound, and the way these errors propagate depends entirely on the mathematical operation. If you are just adding 2 links, their absolute errors simply add together. Not too bad, but if you are multiplying quantities, say to find an area, it's their relative or percentage errors that add up. And if a quantity is raised to a power, you have to multiply the relative error by that power. This is exactly why a tiny, tiny error in measuring the radius of a circle will snowball into a massive error when you calculate its volume. All right, let's shift gears to section 4. What are dimensions, the DNA of physics? We are going to look at the deeper meaning behind these units. This is where we strip away all the numbers, all the specific measurements, and look at the fundamental nature of the physical world. You see, all physical quantities represented by derived units can be expressed as a combination of our 7 base quantities. We call these base quantities the dimensions of the physical world, and we denote them using these simple square brackets. So regardless of whether you measure length in meters, inches, or light years, its fundamental underlying dimension is simply bracket L. Mass is bracket M, and time is bracket T. It's like the source code of reality. This quote right here brilliantly illustrates how this works. The core rule is that dimensions are completely 100% independent of numerical multiples and constants. They simply show you the basic recipe of fundamental units that make up a specific physical quantity. Let's look at a real example so you can see what I mean. Force is defined as mass times acceleration. Okay, mass has the dimension of m. Acceleration is velocity divided by time, which eventually breaks down to length divided by time squared. By combining these basic dimensional blocks, we create a clear, universal dimensional formula for force, m to the power of 1, L to the power of 1, and T to the power of -2. Finally, section 5, dimensional analysis in action. Let's take everything we've learned and explore why mastering this is a total game changer for checking your work and understanding physics on a purely structural level. It all rests on this simple but incredibly profound rule, the principle of homogeneity of dimensions. It states that you simply cannot add velocity to force. You can't subtract an electric current from a temperature. It's the ultimate apples-to-apples rule. The dimensions must match perfectly for an algebraic equation to have any physical meaning whatsoever. You can only add length to length and mass to mass. Because of that rule, dimensional analysis becomes the ultimate toolkit, giving scientists 3 major superpowers. First, it allows you to prove whether complex formulas are fundamentally broken before you even plug in a single number. Second, you can use it to derive completely new relationships between physical quantities if you know they depend on each other. And third, it acts as a flawless mechanism for converting units from, say, the modern SI system back to the old CGS system. Let's actually test it out right now by checking the famous kinematics equation. Distance equals initial velocity times time, plus 1/2 acceleration times time squared. Step by step, watch how the variables on the right side beautifully cancel out. Velocity times time, the times cancel, leaving us with just the dimension of length. Acceleration times time squared, that also mathematically cancels out the time dimension entirely, leaving just length. Because every single term on the right-hand side equals the exact same dimension of length as the distance on the left-hand side, we have proven the equation is dimensionally consistent. It's kind of like magic, but it's just pure logic. But, and this is a crucial word of caution, dimensional analysis definitely has its limitations. It entirely ignores constant numbers. Think back to that last equation we just did. The fraction 1/2 has absolutely no dimensions. So dimensional analysis can't tell you if that 1/2 is supposed to be there or not. Therefore, an equation might have perfectly correct dimensions, but still be physically incomplete or entirely false. Dimensional equality is necessary, for sure, but it is not sufficient on its own to prove a relation is true in the real world. And there you have it. With the strict rules of precision, error propagation, and the DNA of dimensions thoroughly mastered, you now have the absolute foundational bedrock required to accurately measure the universe. You are no longer guessing, you are quantifying. So, equipped with these powerful tools to measure reality itself,